Okay, so this is a part B to the lecture that we had yesterday, so to finish up the last few slides. And this was the last, uh, excuse me, this was the last slide that we got to where we were looking at SN2 reactions in the preparation of some useful pharmaceutical materials. And so, for example, here you had the amino alcohol, because we got an amine and an alcohol in there, reacting with this dialkyl halide. So this is 1,2 dichloroethane, and you can actually make the new carbon-nitrogen bonds that you need fairly easily using this method, and you get what's known as ethanbutol, trade name myenbutol, which is useful for a variety of lung ailments. And again, we talked about the fact that oxygen can also behave as a nucleophile, but it turns out that the nitrogen is the nucleophile in this particular reaction, because nitrogen, being less electronegative than oxygen, is more willing to share its electrons and form a bond. We also had the example down here where we took this primary alkyl iodide, reacted it with methylamine, made the needed carbon-nitrogen bond, and then through a step that we might learn about later, made Prozac. In just a couple of steps, you can make Prozac, and it's pretty amazing that you can make this very, very expensive drug. Well, it's not terribly expensive, but I mean, it generates a lot of revenue every year for the company, and in using just sophomore level organic chemistry. So there are also alkyl halide equivalents that are in biological systems. So if you were to study the physiology of a variety of biological reactions, you would find that there is actually not any alkyl halides in our body, at least to any appreciable extent. You won't find methyl iodide, you won't find methyl bromide, you won't find methyl chloride. However, our biological systems actually do methylation chemistry using a molecule that's known as SAM, or S-adenosylmethionine. And if you look at this, what you see is you see this methyl group that's highlighted here in this beige box. It's attached to a positively charged sulfur. And it turns out that this positively charged sulfur is actually a pretty good leaving group. So this entire thing that you see here, that I'm circling right now with my mouse, okay, that is the biological equivalent of iodide, okay? It turns out that biology just couldn't make methyl iodide, and it's not particularly soluble in the bloodstream, which you would imagine that an alkylating agent that biology needs would have to be water soluble. But S-adenosylmethionine actually is water soluble, and it is a methyl iodide equivalent for biology, basically. And so nucleophiles can react with SAM, and you can methylate the nucleophiles, and then the sulfur species, or the sulfide that gets generated, is actually a pretty decent leaving group, and that can get recycled through a variety of biological processes. Now, this turns out to be pretty important because if you think about adrenaline, so if we look down here at the bottom, you take norepinephrine, which has a primary amine, which is a nucleophile, and react that with SAM, that gets methylated, puts a methyl group on the nitrogen, and now you have epinephrine, or adrenaline. And you all know that adrenaline is very important in our fight or flight response that we have as part of our processes that we have to for our safety. And so once we detect some type of stress or danger, that sends a nerve signal down to the adrenal gland, where this process actually occurs. And it turns out that this is actually pretty important because you don't want adrenaline in the body all the time, or you would be in this fight or flight response all the time. You'd have an increased heart rate, you'd have increased blood pressure, you'd have increased dilation of your lung passages to bring in more air, more glucose would be synthesized. You wouldn't live very long if you were in this fight or flight response all the time, because you'd just be wearing your body out. And so the body makes this on demand. As you need it, it gets synthesized. And the way that the biological system does this is through methylation of norepinephrine. And what's kind of interesting here, I know we've talked an awful lot about this particular drug, methamphetamine, but if you look at adrenaline, it's got a lot of the same features of methamphetamine. And so, as you can imagine, meth works in the brain, and so does epinephrine or adrenaline. And so, there's a lot of similarities between a lot of these drugs. And so, that's why they work the way that they do. So, this is something for my biology friends, for those of you who are in biology, studying biology, just to show you that these SN2 reactions and the substitution reactions that we're learning about actually are biologically relevant. The other mechanism that we need to talk about is the SN1 mechanism, and this is the one where the leaving group first leaves through the slow step to give us the carbocation. It makes sense that that's the slow step because we're going from something that has an octet to a species that does not. And so you can't bottle this. It's what we call an intermediate. It just exists for a very short period of time. And then some nucleophile, in this case, they're showing the acetate anion as the nucleophile can come in and attack in a fast step to form a new carbon-carbon bond. So if you look at this particular overall reaction, what we're doing is we're taking an alkyl halide, which happens to be tertiary, and we're reacting it with acetate to make an ester. So we can, that's another functional group transformation that we can do. So even though it's SN1, again, don't confuse the one for the number of steps. This actually has 2 steps. The slow step here is the formation of the carbocation. So this is the energy of activation for that first step. You can see that the carbon-bromine bond is breaking. Once it is broken, you have the carbocation that sits down here in this shallow well that is actually elevated from the products and the starting materials. So it's an intermediate, and then it goes through a second transition state where the nucleophile reacts with it through a smaller energy of activation. So you can see the energy of activation here is quite small compared to the energy of activation of formation of the carbocation, and then that goes down and forms the product. So carbocations are, for the most part, trigonal planar. They are sp2 hybridized. They have a vacant p orbital. The p orbital has no electrons in it, and so we generally think of it as having the positive charge, although it's the whole species, it's positively charged actually. But that carbon, we say, has a positive character to it, and so you would expect that the bond angles would be 120 degrees. If we take a chiral tertiary alkyl halide, here we've got a bromide, we've got a CH2D, a CH3, and a CH2CH3. So an ethyl group, a methyl group, and a deuterated methyl group. So this is a chiral center. When the leaving group leaves, if we imagine that leaving group completely leaving and getting totally out of the way, we would have a trigonal planar carbocation, okay, shown here. And the nucleophile would have a 50-50 odds of attacking either from the left or from the right. And if it attacks from the left, you would end up with enantiomer B. And if it attacked from the right, you would end up with enantiomer C. And what you would find is that if the leaving group got completely out of the way, you would end up with a racemic mixture. So you would start off with a very expensive chiral starting material, and you would end up with a very cheap product, and you would lose your job if you were actually trying to do chemistry like this in industry, because starting with expensive starting materials and producing cheap products is not a great way to make a profit. So this is a process that actually racemizes that chiral center. So we learned that SN2 chemistry, you completely invert the stereocenter, but with SN1 chemistry, we can racemize and get racemic mixtures because of that trigonal planar carbocation. The probability of attack from either side of the carbocation is 50-50. Now let's look at a real example where you could start off with a molecule like R minus 2-bromooctane. The minus just means that it rotates plane polarized light in the negative direction, so don't worry too much about that. But just R2-bromooctane. You can see the hydrogen, the bromine, the methyl group, and then the other alkyl group. We've got some stereochemistry, so you can figure out that in fact it is the R stereochemistry. And if we take this and place it in water, water can function as a nucleophile. And we can allow this to work through an SN1 reaction. This is known as a solvolysis, by the way. because the solvent, water, is actually responsible for some of the chemistry. And so anytime your solvent is also a reactant, we call these solvolysis reactions. And so notice we're going from an alkyl halide to an alcohol. But notice here, this is pretty interesting. So this is an SN1 reaction because water is a weak nucleophile. Okay, and you end up with S2-octanol in 83%, and you end up with R2-octanol in 17%. This is not 50-50. This is actually, it looks like we went through some inversion, right? So we have the R stereochemistry here, and the majority of the product is actually the S stereochemistry. So does that mean that this reaction was going through both an SN1 and an SN2 reaction? No, it was completely going through an SN1 reaction. And remember what I said on the previous slide was that the leaving group had to get completely out of the way. Well, that is not always the case. And so if you imagine our molecule being represented like this, where the red sphere here is our bromine and these other colored spheres are just the other groups. When the leaving group leaves, it can only leave from one face. And so you get the trigonal planar carbocation, but on this side is still the leaving group. If it hasn't had a chance to get completely out of the way, one face is going to be blocked. And so what that means is that the nucleophile coming in from the top is unhindered, but if the nucleophile tried to come in from the bottom, it would have to run into that negatively charged bromide. And so what you end up with is more than 50% going in this direction, because this is a lot easier for the chemistry to occur. And this, since this has to interact with another negatively charged species, you're going to form this one in less than 50%. Okay, so we need to know something about carbocation stability, and what we know about carbocation stability is that the more substituents we have around a carbocation, the more stable. So a tertiary carbocation is actually quite stable. The secondary is okay. Primary is not stable at all, and neither is methyl. And you can see that through these electrostatic potential maps. Blue, remember, means positive charge, so you can see there's a lot of positive charge on this carbon atom for a methyl carbocation and a primary carbocation, but it becomes more and more diminished as you go to a secondary and tertiary carbocation. So that means that that positive charge has been diffused throughout the system. So the more alkyl groups you have attached to the carbocation, the more stable it's going to be. Okay, and so that has an impact on what we call the Hammond postulate. And so basically what this says is the more stable the carbocation, the faster the reactions go. So basically in the book, what the Hammond postulate tells us is that the energy of activation, or the slow step at the transition state, is going to look most like the species that is closest to an energy. And I'll talk a little bit about that tomorrow in class. So we'll bring up the Hammond postulate tomorrow. So I don't expect you to completely get that from just this screencast. So the reason that the more substituents you have around a carbocation, the more stable it is through a process known as hyperconjugation. And so if you look at a methyl carbocation, there's no groups out here that have sigma bonds that can kind of overlap with the carbocation and help stabilize it. Because all of these carbon-hydrogen bonds are in the plane of the node, if you will. However, if you look at in this case, we were looking at a secondary carbocation because we've got two alkyl groups attached to it. You can see that these carbon-hydrogen bonds, being sp3 hybridized, they kind of look like lopsided p orbitals in a way, and they can actually donate some of their electrons into the carbocation and help stabilize it through this process that we call hyperconjugation. It is not a resonance stabilized structure. It is truly a through space